All right, we're ready to start counting, but we need to figure out how we're going to count certain things. So remember when I said, and so there's 4 basic structures, although some counting problems involve some mixture of those. So it's not always going to be one of these, right? So we have order matters, and we have order no matter, right? We also have repetition allowed, and we have repetition not allowed. Okay? So these are the 4 major things that we are going to try to count. And then realize that problems rarely come out so nice and neat and will involve some combination of them. No pun intended. Okay, so this is what we're going to try to fill in. All right? Now, these are, let's be clear. These are 4 major things if we are working with indistinct objects. If we are not working with distinct objects, and we will look at those cases, then we'll have to adjust, okay? But if we're working with indistinct objects, and then we want to count, and we want to consider order mattering and not mattering, repetition allowed, not allowed, these are going to be 4 things we try to address, okay? So the first of which is going to be a permutation of distinct objects. Okay? So, what is a permutation, you ask? Well, a permutation is, what it is means you are considering the order. It's like an arrangement. So here the order matters, and repetition is not allowed. Okay? So if I take 6 of you and I want to arrange you in a line for a picture, once I use one of you up in a spot, I can't use you again. You can't be in the front and the back of the line, right? You are used up in your spot. So that's what I mean by repetition is not allowed, but where you are in this line does matter. Okay? So the permutation, order matters, and repetition is not allowed. So let's look at an example. So we can permute all of the distinct objects or some subset of the distinct objects. So let's start first with all of them. Okay, so let's say we have these letters. Okay, so I have 5 distinct objects. So our first question is, how many permutations, which also would have come up in discrete math, how many permutations of these 5 objects? Well, you can split this up into our steps from above, right? We could say, in the first step, I have 5 letters to choose from, right, at the very beginning. Maybe I chose an X first, but I had 5 choices. Well, once I've chosen that X, I now have, for my second letter, 4 choices, right? And then I have, after I've used 2 letters, I have 3, and then 2, and then 1, right? And that happens if I take all of these and I permute them, which comes out to be, you should all recognize, as 5 factorial. Does everybody agree? Is that unclear to anybody? Okay, so let's state this. So the number of permutations of n objects is n factorial. We looked at an example right there of 5 distinct objects, but here we are going to say in general, if you have n, then you should have n choices for the first letter, then n minus 1, all the way down to 1. Now, what if instead I say how many permutations of size 3 from these 5 objects? Okay, well, what worked for us before, let's try it again. We have three steps this time. Choose the first letter, then the second, then the third. At the beginning, I have 5 choices. I use up 1 letter. I then have 4, and then I have 3, right? This is not equal to 5 factorial, nor is it equal to 5 factorial minus 2 factorial. But what is it equal to, since if I want to try to write these in terms of factorials? Anybody see? That works, right? So then this becomes 5 factorial over 2 factorial. What does that have to do with 3? Well, this was what's left, good, after I performed the 3 steps. So really, it would be better if I wrote 5 factorial over 5 minus 3 factorial, right? Yes. Okay. So in general, let's write this down. The number of permutations of n distinct objects, this should say distinct, let's put that in there. This time we say taken r at a time. What is that going to be? I'll hear the kittens, they're wrestling. Yes, Dennis is the only one that's talking to me today. Shreya did, and Tommy. Okay, so what is it? It's n factorial over n minus r factorial. Good. And we often denote this, our shorthand is NPR. Your calculator might do PN comma R. This is my favorite. It is not choose though. Choose goes specifically with combinations. Okay? If I want to, working with n distinct objects, we're going to say taken r at a time. The one that we just found was order matters, repetition not allowed, n factorial over n minus r factorial. That is that corner. Okay? Okay. Now, what if, consider this, okay? Okay, so here I have 6, but they are not distinct, okay? So whatever I just did up here is not gonna, I'm gonna have to figure out how that affects things, how that changes things. if they were 6 distinct objects and I wanted to know how many arrangements of these 6 objects. Okay, that becomes our question, right? So if you are trying to sort it out and you're like, well, above when it was 5, it was 5 factorial. If they were distinct, I know it would be 6 factorial, but I know it's not 6 factorial, right? Because that doesn't work. And so I asked myself, what's actually happening? Well, if we secretly put one of them blue, then every arrangement like that we pick of these letters, it's going to overcount by how many? Right, so having a T, 2 E's, X, A, S, yeah, we're doubling this count, right? We're overcounting by 2. And only by 2, right? It's like we move them all around, but we just happen to be counting those, every arrangement of the letters twice because we're counting every time the E's change places. So we could say that, and everybody feels good about that. Yes? Okay. All right. What about so you're like, I know what I'm doing now. How many arrangements of these 7 objects? We know we can start with all 7 factorial, but we know we're overcounting, right? Because we're overcounting by how many? Good. It's not by 3. And see, it's not by 3, just like it really wasn't by 2, although it was by 2. It was by all the permutations of those 2 letters, which happened to be 2 because 2 factorial is 2. So what we're overcounting is every arrangement like this and then all the permutations of the E's, right? Of which there are 3 factorial. So we're going to divide out that 3 factorial. You tell me. Do we have 8 here? Yeah. These 8 objects. So I'm going to write down, yep. One might do this, and somebody in my last class did that, which is not correct. Whereas this one is correct, right? So these E's and the A's are not the same thing that's getting permuted. We find all the permutations of the E's, and then for each permutation there, we have to run through the permutations of the A. So we think of like this tree, right? You first place all the 8 letters, and then they're running through all the permutations of E, and then each one of those E has a permutation of the A's. So you're overcounting by that product of 3 factorial times 2 factorial.